Okay, hello. So my name is Jonathon Smith, and I work in the Mission Design and Navigation section at the Jet Propulsion Laboratory. For those of you not familiar with JPL, we do a lot of work with NASA's deep space robotic missions. And today I'm going to be talking about an in-house software set that we built called the Mission Analysis, Operations, and Navigation Toolkit Environment, otherwise known as Monty Python. At JPL, we use Monty primarily for deep space navigation, so we use it to fly NASA's probes to wherever they're going in the solar system. That's why this talk is titled Monty Python for Deep Space Navigation. I think an equally good title for the talk would have been Astrodynamic Computing with Monty, because at its heart, Monty is really a Python library for astrodynamics, and we'll see what that means a little later on. So I'm going to be talking about, looks like my slide is a little bit messed up, but I'll be talking about three different things today. So one, you've already seen what Monty can do. Two, Monty is a new pillar in the Python computing stack. And three, Monty is a platform on which the aerospace community can grow. So we'll start off with number one. So this is a picture of the Mars Science Laboratory descending down to the surface of Mars in mid-2012. During its 8-month voyage from Earth to Mars, Monty was used for navigating the spacecraft and delivered it safely to this atmospheric entry point that allowed it to drift down to where it was supposed to go. Also, this photograph was taken by another NASA asset at Mars, the Mars Reconnaissance Orbiter. And in order to get this picture, the orbit of MRO had to be phased correctly so that it would be in the right place at the right time and pointing in the right direction to capture this. And Monty was used to do that as well. So this is a picture of Saturn taken by the Cassini spacecraft with Saturn's moon Titan in the foreground. Cassini has been at Saturn since 2004, but ever since 2012, Monty has been used to navigate the what's called the Cassini Solstice mission. And during this time period, so from 2012 until now, Monty has been used to successfully guide Cassini through several dozen satellite encounters, close encounters, and also design over 100 orbit trim maneuvers that keep Cassini flying on course. So this is a more recent picture. I think it was taken last week of Jupiter and 3 of its moons, Io, Europa, and Ganymede. And this was taken by the Juno spacecraft, which made headlines on the 4th of July after successfully inserting into orbit around Jupiter. So that Jupiter orbit insertion burn that placed Juno off its interplanetary trajectory and into orbit around Juno was designed using Monty. And indeed, the entire 5-year cruise period of Juno from Earth to Jupiter was navigated using Monty. So I want to take a step back. These are all pretty recent missions. I want to take a step back to give a little context as to where this software has come from. JPL has been very involved with the solar system exploration for quite a while, and in the early 1960s, there was a team of engineers at JPL led by a gentleman named Ted Moyer that built a program called the Double Precision Trajectory and Orbit Determination Program. So it's a little bit of a mouthful. And this program was used to navigate the golden age in deep space exploration. So that's kind of indicated by this little blue blocks down here. But it was used to navigate the Mariner and Pioneer missions, the Voyager and Viking missions, Magellan, Galileo, and the early part of the Cassini mission. So it's a very, very successful program. So as time marches on, 60s, 70s, 80s, of course, we got all these advances in computers. So this program was constantly being rewritten. It went through Fortran 4, Fortran 5, Fortran 77, Fortran 95. It was wrapped up in Perl. And by 1998, it was becoming pretty obvious that there was another update was going to be needed to keep this thing current. So this time, rather than just do another rewrite, JPL decided to commission an entirely new project, and that was what eventually became MONTE. And it was going to differ from the DP Traj ODP, as it's called for short, in two important respects. First, it was going to be written in C++, all the core algorithms, C++, and it was going to be wrapped up and presented to the user in a Python API. And this was at a time when Python was still not very well known, and I think that that decision worked out pretty well for us in the long run. The second aspect is that the DP Traj ODP was more or less a dedicated navigation tool, right? So it was used for deep space navigation, not so much useful for anything else. MONTE was designed to be a general purpose astrodynamic library that you could use to do deep space navigation. So that's very important. So MONTE got its first operational assignment in 2007, navigating the Mars Phoenix mission from Earth to Mars. And so you can see it kind of comes online here, and there was a period of time where it overlapped in operations with the legacy software. But around 2012, the legacy software was retired, and MONTE now powers all flight navigation services at JPL. So right now, MONTE is being used to fly the Dawn mission, the Juno mission, Maven, MRO, and SMAP, which is an Earth orbiting mission, and I'm probably forgetting one or two, but so yeah, so all the missions right now are flying with MONTE, and it's also being used to design the next wave of missions that JPL is going to be sending out over the next decade. Okay, so going to move on, and I want to introduce MONTE as a new pillar in the Python computing stack. So what I mean by that is there are a lot of libraries in Python that are dedicated to doing computation for certain specific fields. So you have scikit-learn for machine learning, you have pandas for data analysis. And the way I like to think of MONTE is as kind of a new entry, a library for doing astrodynamics. So I've been talking a lot about astrodynamics, and I haven't really explained what I mean by that, if you're not familiar with the term. So celestial mechanics is the study in general of how bodies move through space. Generally, when you're talking about celestial mechanics, you're talking about planets or stars, things like that. And astrodynamics is a specialization of celestial mechanics that deals with how man-made objects move through space. And there are two important differences between man-made objects and larger planetary bodies that make astrodynamics a little bit different. So first of all, when you're flying a spacecraft, it's pretty small, right? So it's being acted on by the gravity fields of other planets, the sun, but it is not exerting gravity interactions with those bodies. So it's just kind of being pulled around. Also, because it's so small, the spacecraft is subject to a lot of perturbing forces that you really don't have to worry about when you're looking at how planets move. So if you're operating in the vicinity of a planet, for instance, you're going to have atmospheric drag on your spacecraft. There is the pressure of sunlight hitting your spacecraft, which can actually push your spacecraft off course. There are outgassing effects, so when you first expose material to the vacuum of space, it's going to shoot off gas, and that can push your spacecraft. If you have heat, like a heat source on your spacecraft, you get thermal radiation. And of course, the big one is maneuvers. So spacecraft are maneuverable. You can fire rocket engines to change their course. So MONTE is particularly well suited for astrodynamics, but it can also be used in a more general sense for celestial mechanics. So the Solar System Dynamics group at JPL is a group responsible for publishing the trajectories of all the major bodies in the solar system, including the satellites and comets and asteroids and things like that. And they're using MONTE for some of their work, so it generalizes pretty well. So, you know, I'm presenting MONTE as a general purpose astrodynamic library, but the fact is at JPL it's primarily been used for deep space navigation, so it happens to be really good at deep space navigation. And there are kind of three interrelated components involved in navigating a spacecraft in interplanetary space, and they kind of correspond to the stage in the mission at which they're executed. So before you launch a spacecraft, you have to design, so in the mission planning phase, you're going to have to design the orbit that's actually going to take you to where you're going. So you're starting at Earth, you're going somewhere, you have to figure out ahead of time what that path is going to look like. And you're going to want to do it not only to get your spacecraft to the destination, but also to put it there at the right time and the place to take the right science measurements that people want to see. Now, a lot of times you're going to do this and you're going to try to optimize under a certain cost function, for instance, the amount of propellant used to get you to where you're going. So you're going to want to try to keep the propellant usage down to a minimum, which makes your spacecraft lighter, which makes it easier and cheaper to launch. So after you've designed your planned trajectory, you actually have to fly it. So the spacecraft launches, and it gets hit with all these perturbing forces, the atmosphere, the solar radiation, all that kind of stuff, and it starts getting pushed off course, right? So the entire time a spacecraft's in flight, you have a team of people that are just trying to keep track of where it actually is. And that process is called orbit determination. So what'll happen is they'll process a bunch of tracking data, they'll figure out where they think the spacecraft is, they'll pass that information on to the flight path control team, and if the spacecraft gets sufficiently far off course, the flight path control team will design a maneuver to bring it back together. So Monty has a lot of dedicated systems that are particularly well suited to these different problems. I won't go into all of them right now, but I do want to emphasize that even though this is where Monty's primarily been used and where it's been proven, it's definitely not limited to only solving deep space navigation problems. So this brings us to number 3. Monty is a platform on which the aerospace community can grow. So the basic pitch for using Monty as a platform involves the tremendous amount of infrastructure that you need in place just to get started in studying astrodynamics. So before you can design a trajectory, you need to be able to represent trajectories. You need to be able to query them to get the state of the spacecraft at different times. You need to be able to define coordinate systems and rotate coordinate systems to search through trajectories for different astrodynamic events like closest approach, things like that. You also need to do, calculate a lot of partial derivatives if you want to do optimization or, filtering, things like that. So the idea is to use Monty as a starting point for whatever astrodynamic problem you're working on, and then just focus on the actual part that you want to do and leave the rest to Monty to handle. So some examples of where Monty, I think, could really excel outside of the deep space navigation field is, number 1, Earth-centered navigation. It actually does this right now. Monty's flown missions around the Earth, and it's also flown missions to the Moon. So it's already been proven, but I think more generally it could be used for like weather communication satellites, for constellations of satellites in low Earth orbit, things like that. I think it'd be really useful in doing collision avoidance analysis. So this is where you have a spacecraft and you want to make sure it doesn't run into anybody else's spacecraft. You have non-cooperative rendezvous situations where you're trying to rendezvous with a target, maybe a malfunctioning satellite that is not trying to rendezvous with you. And then you have the cooperative rendezvous, like docking a cargo ship to a space station. So these are just some examples of problems outside of the deep space nav field where I think Monty would be particularly well suited. So unfortunately, Monty is not open source. This is for a number of reasons. In fact, it wasn't even available to license easily until just the past year when it was released from ITAR restrictions by the State Department. If you're not familiar with ITAR, it's I think it's the International Trade and Arms Regulations. It's code that the State Department used to make sure that countries we don't want getting our technology don't get it. So Monty was kind of released from those restrictions. It's still subject, the source code is still subject to some restrictions which prevent us from making it open source, but we are eager to license it out for classroom research and commercial use. I'm particularly excited about using Monty in the classroom, and I think that really the idea here is if you're teaching like an orbital mechanics class or a space mission design class, you can create assignments that actually explore the lecture topic and again, delegate all of the infrastructure to Monty. So if you want to look at like the difference between 2-body and 3-body motion, you can just create a 2-body trajectory with Monty and integrate a 3-body trajectory and difference them. If you want to build your own integrator, you can compare it to Monty's integrator under different force models, things like that. I think for research too, Monty is already being used for research at a number of different leading aerospace schools. So here at UT Austin, they have a copy of Monty. At CU Boulder, up in Colorado, they have a copy. At Purdue, and a number of other ones. And again, I think, use Monty to start as a starting point for your investigation and focus on what you want to do. So I'm working on a research project with a professor here at UT, looking at using polynomial chaos expansions to do nonlinear mapping of uncertainty in deep space. And again, this is great because we don't have to build our own integrator, our own trajectories and coordinate frame systems. We can actually concentrate on what we want to do. Also, I think it's great that using Monty, you're going to be speaking the same language as other researchers. So, I mean, they've already started using it here at UT and CU, but of course at JPL, we're a world leader in doing astrodynamics, so you'd be speaking the same language as JPL. And I think that would make collaboration a lot easier. And for commercial entities, I think that Monty has particularly something peculiar to offer in that it's so tested and proven in actual flight missions that I think it provides a compelling argument if you're going to build your own operational infrastructure to start with something that already has proven itself. And again, because it's Python, you can kind of own your software, right? You don't have to be constrained by somebody else's workflow. If you want to put up Monty on a backend server and create a Java and JavaScript front end and run it from your browser, you can do that. You can do all the things you'd like to do with Monty in that sense. So for more information about how to get a copy of Monty, you can go to our website, montypi.jpl.nasa.gov. There's not a lot of content there right now, but we're hopefully going to be updating that in the next few months. I want to give a special thanks to NASA's Multi-Mission Ground System and Services Program Office, who are our main sponsor for Monty, and also all the flight missions that are using Monty that also give us a lot of support too. Also want to thank the Monty development team. And before I let you go, I just kind of want to give the last pitch that, if I think Monty can bring Python to the aerospace community in a bigger way than it has been previously. So if you know a professor that's doing aerospace research, or you know a guy that's working in a company, maybe just let them know that there's a Python solution out there that they may want to check out. So thanks, that's all I have. Any questions? So, right. So for the very long time, JPL's used a Diva integrator. It's a name given to a particular kind of integrator. We've had requests lately to generalize, kind of make it plug and play, so you can kind of swap out your own integration algorithms. So we've added a new one just recently, and I think we're looking to generalize out to allow someone to kind of stick in their own black box integrator into that system.
Can you give us any idea of what it's like to use it?
Right, yeah. So for those of you that are disappointed that I didn't show any code, I actually have a full narrated example of how you can use Monty to explore the Voyager 2 trajectory in the paper that's going to be published in the proceedings. So that, I think it fit better in that context because I can explain. And it also goes into the core systems of Monty, what's available, and a little more detail about how the library actually works. So. Yeah.
Is Monty pure Python, or does it use any of the older, I used to work on Fortran code.
Right. Yeah, so all the Fortran code from that double precision trajectory and orbit determination program, that original program, has been rewritten into object-oriented C++. So the majority of Monty's core algorithms are C++. They're wrapped up in Python. But then there's a whole supporting infrastructure, too, that's been built around it in pure Python. Yep.
I wonder if you could just comment on the comparison between what you're doing with Monty versus, for example, GMAT.
Right. So they're somewhat similar. GMAT is for those of you who don't know, GMAT is an open source project led by Goddard Space Flight Center that does similar things to this. One of the main differences between GMAT and Monty is GMAT's primarily a design tool, where Monty also does design and also has been used in flight. So I don't think GMAT has very robust orbit determination or flight path control support. And also GMAT is primarily meant to be used inside of an application window, similar to, it's more of a program. It does have a library you can interface with, but Monty is more, the prime API for Monty is just Python. It's a Python library, and you can build your own, PyQt interfaces if you want, but they're not even provided for you. So Monty, I think Monty tends to be a little more lower level in its general use case.
How large is the code base roughly?
So I think we're at about 800,000 lines of, logical lines of code in C++, and probably about twice that in Python, in pure Python, something like that. So yeah, it's a fairly old project, I guess 15 years or so now that it's been kind of under wraps, and we're just now trying to get the word out about it. So, any other questions? Yep.
Quick follow-up. You mentioned that it's recently been freed from ITAR. Is there any prospect of it being taken fully open source in the future?
So that's very complicated right now because there are certain aspects of the code, the source code, that are controlled by the Commerce Department. So in order to make something like that happen, we'd kind of have to refactor the entire code base, and I'm not optimistic about that happening anytime soon. Also not optimistic about supporting Python 3 anytime soon, which is unfortunate. But I think that both of those are possibilities in the future, as maybe, and they can maybe even coincide as we make the switch to Python 3, take a look at our source code. But again, it's a lot of cost for limited benefit to people at JPL, so it's hard to make the case. So the Commerce Department has its own export control statutes, right? And you get labeled an ECCN, which is an export control classification number, and so. No, that's just the cost of doing business in the United States is that certain technologies are regulated. So it's not that they sponsored it. It's just like the State Department can just say, if you work on this, you can't export that kind of thing. Yeah. Yeah, it's just the statute regulations in the United States. Yeah. Okay.
No other questions? All right, thank you.
All right. Thanks.